Okay, right now we're going to look at the wave nature of light. Anytime you think of waves, you might envision something along the lines of this continuous pattern where it's just, you have these crests. These are crests. This is a trough. The distance between one crest and the next is the wavelength. Wavelength. This is a length or a distance, so you might look at units of meters or nanometers, which we saw in the previous video with Bohr's model. When we look at wavelength or equations, we actually use the the Greek letter lambda, and this is for wavelength, always. So anytime you see lambda, we are talking about wavelength. Additionally, you might see frequency. So we use the Greek letter nu for frequency. And this is the number of waves that pass a specific point per second. Okay. So something to conceptualize here is that if you have this wave right here, it has some set wavelength, and the frequency is going to be dependent on that wavelength. What if we squish these waves together so that now we have a shorter wavelength? We have squished the distance between these two waves, so now it's a little shorter. That means that more waves can pass through that specific point per second. So a trend that you'll notice is that an increase in frequency, and I'm just going to write nu, increase in frequency is equal to a decrease in wavelength. Okay, that is because they are inversely related or proportional, based on a very specific equation. And that equation is C equals lambda nu. C is going to be a constant. C is the speed of light in a vacuum. And the speed of light in a vacuum is always going to be 3.00 times 10 to the 8th meters per second. Okay, so this is a constant that you're going to want to actually remember. You're going to be using it pretty frequently when we're talking about the nature of light. So what can happen what can we do with this information if we have the speed of light and if I give you the wavelength of some type of radiation? We can actually determine the frequency. Okay, so let's try a practice problem in which we do just that. So I will rewrite the equation. C equals lambda nu. This is C equals 3.00 times 10 to the 8th meters per second. Lambda is wavelength and nu is frequency. So what if I gave you a frequency? Oh, I think we're going to do, well, it doesn't actually matter. I can give you the frequency and you have to find the wavelength, or I could give you the wavelength and you have to find the frequency. So I'm going to give you a frequency of 3.2 times 10 to the negative second. Now the units for frequency, there's quite a few of them. It's typically waves per second, or it might just be the number 1 over second, which is the same thing as seconds to the negative 1. Or you might have hertz. So if you've ever had like an old-fashioned radio, the frequency, when you change the dial on the radio, those are hertz. Those are that's the measure of frequency there. Okay, so our frequency here is 3.2 times 10 to the negative 2. And I want us to find the wavelength. All right, so how would we do that? How would we solve for wavelength in this case? Well, first I would change this equation to isolate wavelength. And to do that, you would divide by frequency. So c over nu equals lambda. And in this way, I can plug in my numbers for the speed of light and for my frequency to figure out lambda. So my speed of light, so here's lambda equals 3.00 times 10 to the 8th meters per second divided by 3.2 times 10 to the negative 2, and I'm going to use 1 over seconds. Now the reason I did this is because now that I have seconds here and seconds here, they'll cancel out. Which makes sense because now my unit is meters over 1, same thing as meters, and this is wavelength. So we're looking for a unit of distance or length, and meters meets that requirement. Remember that when you are doing scientific notation and you have a division problem, you do the coefficients, so 3.00 divided by 3.2. You can do that on your calculator. I think you might be able to see this, 3.00 divided by 3.2. And that gives me 0.9375 times 10. And with division, you do 8 minus negative 2. And when you have minus negative, that is the same thing as addition. So 8 plus 2 is to the 10th. And this is going to be meters. Note that this is not correct scientific notation, so we're going to move that decimal place so that we have 9.375 times 10 to the what? This number got bigger, so this number needs to get smaller. 10 to the 9th meters. We're still not quite done because remember, we will always be looking at sig figs. And here we have 3 sig figs and here we have 2. So we need to round this to 2 sig figs, in which case we get 9.4 times 10 to the 9th meters. So radiation that has a frequency of 3.2 times 10 to the negative 2 waves per second, or hertz, is going to have a wavelength of 9.4 times 10 to the 9th meters. Keep in mind that if I gave you the wavelength, you should still be able to find the frequency. Keep track of your units to make sure that you end up with the correct units and the ones that you are looking for. Okay. There will be some additional practice problems listed for you on the website. Make sure to take a look at those and feel free to practice. If you have any questions, let me know. The next video is going to look at the particle nature of light and how we figure out how much energy a particular radiation or wavelength or frequency of radiation has.